All right, section 1.5 is on exponential functions, and the good news is most of this should be review. We will cover what an exponential function is. We'll cover properties of exponents, which will be a review. We will analyze exponential functions, which is kind of combining the first 4 sections as we look at the graphs, and then we'll review how to solve some special types of exponential equations. So to start with, we will just review the definition, and that would be a function with a base b that is positive and not equal to 1 in the form of f of x equals a times b raised to the x. So should look familiar. We've got our coefficient a, our base of the exponent b, and the exponent itself x. So the power b raised to the x has meaning for all real exponents for all b's that are positive. So b is always positive, so we always need to have a positive base. And then the next section here, properties of exponents. This should definitely be reviewed. Over the past couple of years, you should have seen and done properties of exponents. We will review them, and I'll show you some examples as well, just to get your mind going. So we won't be spending too much time just simplifying exponential expressions, but you will need to remember the properties as we work with some of these functions. So the first one here is not necessarily a property. There's not much we can do to simplify this expression, except for the fact that both terms contain b to the x. So really the most we can do is just factor out b to the x. And then you still have a plus c left in the middle. The next one, b raised to the x times b raised to the y. So when you have the same base but different exponents, you can simplify that by writing them with all the same base b, and then you add the exponents. So this would be raised to the x plus y. And then an example of that, so I'll put examples out here to the right. So say I had x cubed times x to the 4th. That would equal x to the 3 plus 4, or x to the 7th. You might also have a base that is a number and not necessarily a variable. I could switch it up, and I could have 4 to the x times 4 to the 2x. So to simplify that, I would keep the base of 4 and then add my exponents. 1x plus 2x is 3x. So that works in both of those situations. All right, the next one is when you have a power raised to a power. So you see we've got b to the x raised to the y, and to simplify that, you would simply multiply the powers together. So that would simplify as b raised to the x times y. And an example of that, say we had x cubed raised to the 4th. That would just be x to the 12th. You multiply a power raised to a power. The next one is when you have a fraction with exponential expressions where the bases are the same. So again, the base has to be the same, and then you subtract the powers from one another, which would be the opposite of that one. So here, when you're multiplying, you add the powers right there. When you're dividing, you subtract the powers. So that would be b raised to the x minus y. And an example there would be x to the, so we'll just stick with 4s, over x to the 7. So I would subtract 4 minus 7. That would give me x to the negative 3. And I'm hoping you all remember that a negative exponent means we should rewrite it with a positive exponent, and that would turn into 1 over x to the positive 3. Or you can think of it as find when you've got a fraction like this with exponents in the same base, the larger exponent is down here in the bottom, so just subtract 7 minus 4, and since 7 was larger, that's where your variable remains with the new exponent of 3. So that's a quick review on some of our properties of exponents. So with this next example, we're going to start combining what we learned earlier in this unit with what we already know about exponential functions. So what we want to do here is give the end behavior of the following functions, and I'd like you to do that using limit notation. So we're going to use what we learned about limit notation from the last section and talk about end behavior again. So I should have said that on here, limit notation. All right, so in order to talk about the end behavior of a function like this, we need to know the general shape of a graph. So what I would do, if I didn't give you any other directions, I'm hoping what you would do is graph that function and draw a quick sketch, and then you've got everything you need to talk about the end behavior. So if you get your calculator out, type in your y equals 7 raised to the x, and you'll get a function that looks like something like this. So we can talk about end behavior pretty easily here. If you look at the positive end of the graph as x is getting larger and larger, that function, the y value itself, is going to increase without bound. That means that it's approaching infinity on the positive side. So we would use limit notation to describe that. So the limit of f of x as x approaches infinity, and we said that would be infinity. And then if we look at the end behavior on the left side of the graph, this function is going to be approaching 0. And if you're not sure if it's approaching 0 or maybe some other value, you should use your table like I showed you in 1.4, and you can plug in different negative x values, farther and farther negative, and you'll see that this is approaching 0. So the function is approaching 0 on the left end. So we would write the limit of f of x as x approaches negative infinity is 0. So at this point you can pause and finish the rest of these. One thing that I like to encourage students to do is, now that we know the general shape of this graph, 7 raised to the x, think about what it might look like if it's 0.7 raised to the x. So instead of taking the number 7 and multiplying it by values, we know that when we take 7 and raising it to a power, we're multiplying 7 by itself. It's going to get very large very fast. So think about what would happen if I've got 0.7 and I'm multiplying 0.7 by itself over and over. That number is going to get very small very fast. So this graph, hopefully you won't be too surprised when you do graph this, and you'll see that it actually is larger when x is negative, very large when x is negative, and it very quickly gets very small when x is largely positive. So after you do that, you can go ahead and write the limit notation for the end behavior for these, and then you can check back and make sure it lines up with my work. Okay, so here are the rest of those all filled in, just the general shape of the graph and then the end behavior for each one. What I'd like you to notice for examples like these are the general shape of the graph based on the coefficient of our base. So the base is whatever is being raised to a power, and then the base itself. So with a base that is ever less than 1, like in example B and example C, when you take a number that's less than 1, so think of a fraction less than 1 or a decimal less than 1, and multiply it by itself over and over, it's just going to get smaller and smaller. So it should make sense that the general shape of those graphs is decreasing and getting smaller. When you have a base that's larger than 1, you're taking a number and multiplying it by itself over and over, so it's going to get very large very fast, like in example A. But if you look at example D right here, our base is positive, so you anticipate it getting very large very fast, but it's being multiplied by -2. So we would typically think the function would look like this, But because our coefficient is -2, it's going to flip the whole thing over the x-axis, and it's going to reverse it. So I'm hoping that the actual function rule is starting to connect a little bit with the shape of the graphs that we're seeing. Okay, on this next page, look at things that we talk about when we analyze a function. So when you analyze a function, you're basically giving as many details about it as you possibly can. And that's going to lump all of our first 4 sections together, plus some extra things. So if we think back to the first section of this unit, that's what we started with. We started with looking at domain of functions. So when we analyze a function, we will state the domain. And then right along with domain, we will state the range, which are the outputs. Then in the next section, we looked at the extrema, so maxes and mins. And then in the next section, we looked at intervals that the function was increasing or decreasing. So increasing. And then in the 4th section, we looked at end behavior. And right along with end behavior, remember we talked about asymptotes to describe end behavior, those horizontal asymptotes. So we will talk about any asymptotes as well. And then some things that we haven't touched too much on, but shouldn't be anything new for you. We also would describe any x or y intercepts. So where the function is crossing the x-axis or the y-axis. We would look for any symmetry. So is it symmetric about either of the axes? Is it symmetric about the origin? And right along with symmetry, we can talk about or specify if the functions are even or odd. So those are related. Periodicity is something you would mention. Periodicity. And specifically, that would be for trig functions, which we won't look at too much right now, so don't worry about that. Models. Models would be what kinds of real life things, what kinds of real life things could that function represent? So it's kind of like examples that you could apply that function to in the real world, and then any other special properties. And special properties is kind of like the etc. part of that. Any other things you might want to add. For example, this function is only defined for certain values, or anything that isn't covered in the first 9 things. So down below here, there's 2 pretty simple exponential functions. We're going to sketch a graph of them and then analyze them using using those 10 things above. So I'm going to go through A with you, and then I'm hoping that you'll pause and sketch B and list out all of those parts to analyze the function yourself, just to make sure you've got the process down. So the first thing to do before we sketch the graph would be actually graph 2 raised to the x on your calculator. So if we graph 2 raised to the x, and you can just hit zoom 6 and view it on your normal standard window, you get the general picture of the graph. It looks like it crosses the y-axis at 1, which we will include when we analyze it, but just so we can get an accurate graph there, and also contains the point, let's see, whoops, 1, 2, 2 raised to the first power is 2, 2 raised to the second power is 4. So you can even just plug a few points in yourself for a function as simple as that, and then just draw the basic curve there. Okay, So now to analyze this function. So the first thing we listed here was domain. All right, so input of this function, what x values can I plug in or can I not plug in? Any exponential functions are defined when the base is positive greater than 1 and when the exponent there is a real number. So any real number I can plug in works, so my domain is all real numbers. So using interval notation, we'll write the domain as negative infinity to infinity. Next, we look at the range. So the range of this function would be the output of y values from any of the x values that I plug in. We can see from the graph that this function, in terms of its upper end, it is not going to be bound by any specific value. So it's going to go all the way to infinity, but it is bound in the negatives. It's never going to get lower than 0. It's never even going to equal 0. So the lower bound is 0. It's never actually going to equal 0. So make sure you use parentheses instead of bracket. And it's going to reach infinity. All right, next would be anywhere the function is increasing or decreasing. So this function is only increasing. Only the y values only get larger and larger and larger as you read the function from left to right. So I always like to remind students that we read graphs just like we read words on a page, from left to right. So that's how we can tell from left to right it's only going to get larger and larger and larger. So this function is increasing on the interval. Really, it's increasing on its entire domain. So it's always increasing. So increasing on negative infinity to infinity. Another way to say that, if it's increasing on its entire domain, you can say that the function is strictly increasing. Strictly increase. Sorry, I feel like I'm taking a step back here on writing. This stylus is not doing its best today. So strictly increasing is the same as increasing on the entire domain. Maxes and mins. So any local max or global max, and we can see that because it's always increasing, it's never going to have a max because it's always getting larger. And in the same way, it is getting closer and closer to 0, but because it's growing infinitely smaller, it's never going to get to a lowest point. So there are no extrema. So we would just write no extrema. The next thing was any intercepts. So let's see. Oh, did we talk about end behavior? I skipped end behavior. Okay, so the end behavior here we could write using limit notation, and then we can also represent it using the equation for the horizontal asymptote that determines the end behavior. So we do have end behavior to talk about. So let's talk about the limit of our function as x approaches infinity, and it's unbound. It's going to increase infinitely, so the limit is infinity. If we look at the limit on the left side of the function, as x approaches negative infinity, it's getting closer and closer to 0, and that means we have an asymptote at y equals 0, horizontal asymptote right here at y equals 0. Okay, next, now we can talk about intercepts. So we saw that the function crossed the graph on the y-axis right here at 1. So y-intercept 0, 1. There is no x-intercept. It is never going to cross that x-axis. As close as it gets, it won't cross it. Let's see, we don't have any symmetry, so we're looking for any symmetry with respect to the x or y axis or origin, and that is not a symmetric function, so it's not even or odd. Any models that we could relate to this, we definitely can, because this is a graph of something that's growing exponentially. So exponential growth is super common in nature, so a model we can talk about would be population growth. Is one example, probably the most common for something like that. And then there are no other special properties we need to talk about. So we have analyzed this function. So what I'd like you to do now is go through those 10 things above and analyze this function on your own, and then I'll go ahead and fill in each of those, and you can check back when you finish this example. Okay, so here's all the information after analyzing, the function, okay, let me try that again. How can I change the page? Okay, I've done something I didn't mean to, but I can work with that. Okay, so here's all the information after analyzing that function. And the last thing is models, which I wanted to actually be able to talk to you about. So this function is modeling exponential decay. So that's when something is decaying. It starts off decaying very quickly and then slower and slower. So, and it kind of dies off. So one example of that would be half-life, which many of you have heard about. For decay of certain minerals and things like that. So half-life. Also, population growth is a thing, and so is population decay as certain populations die out. So population decay can be modeled by exponential functions. Decay. And then something I found super interesting is temperature cooling. So imagine baking cupcakes or a pie. You get it out of the oven. It's super hot at first, but it cools in the first 10 minutes. It cools quite a bit, but it stays warm for almost hours. So temperature cooling is modeled by exponential decay. Temperature cooling, which I think is very cool. Okay, so over on that, something called the continuous change model. And the continuous change model is a general function rule that we can use to calculate a quantity. That's if it's growing or decaying continuously at a certain rate, so that rate isn't changing, then we can use this function to determine the amount left after a certain amount of time, t. So that continuous change model looks like this. A of t, so t represents time, p times e raised to the r times t. So I call this the PERT equation because P-E-R-T. So P times E raised to the RT. So I just call it PERT. You might hear me refer to that as PERT in the future. All right, so P represents the initial value. So P represents the initial value or starting point. So the initial value is the starting point. We use P to represent that because it technically stands for principal. So the principal amount is the original amount. So principal amount is P. E represents Euler's number, so it is, you might have learned it as a natural number, it is a natural number, but the E itself is from the mathematician Euler, who kind of normalized that. And that number, Euler's number, has a value of approximately 2.718 2, 8, and that number continues forever. It is an irrational number. The good news is it's programmed into your calculator, so you never have to type in that decimal. You can just type it in E from your calculator, just like pi. Okay, so these examples here kind of talk through the meaning, whoops, man, what is going on? The meaning of PERT, as I like to call it. So what does A of 0 represent? So meaning if I plug in 0 for t right there, meaning no time has passed. That means I'm talking about my initial value or whatever that principal value was. So that means A of 0 represents the initial value. And I'll show you why that has to be mathematically. So if I plug in A of 0, so if I plug that back into this equation, then I have P times E. I don't know what my rate R is, but I do know that 0 time has passed. That means I've got P times E raised to the 0. Well, anything raised to the 0 value or to the 0 power is just 1, so that equals P. So again, just the principal or initial value. When R is positive, remember R represents the rate at which something is growing. So if that rate is positive, then that means that initial value is going to grow. So that represents continuous exponential growth. Continuous exponential growth. So if something is growing at a positive rate, it's definitely getting larger. If R is less than 0, then we say the model represents continuous exponential decay. Okay, so now for an actual example. It says find A of 1 if the initial amount is 100 and the growth rate is 7.2%. So this would say you invest $100 in an account that is growing at a rate of 7.2%, which is super unrealistic. You'll never find an interest rate that high, but let's just pretend. And that would mean I want to find A of 1. So I'm going to plug in everything to this model. P would be 100 because they told us the initial amount was 100. So 100, we always have times E raised to the R times T. So my rate is right here, but you can't write 7.2 because a percentage is not the same as the actual value of that percentage. So percentage, remember you need to move the decimal over twice. So the rate is actually 0.072. So my function would be 100 times E raised to the 0.072 times the amount of time that's passed, which we were told is 1. So this is just plug and jug. Plug all of this into your calculator. 100 times E raised to the 0.072, and you will get the value of about $107.47, which should make a little sense to you because if you start with $100 and your growth rate is 0.072 or 7.2%, think of what 7-ish% of 100 is, which is 7. So you're adding a little over $7 to your initial amount. So in this next example, same general setup here. We've got find A of 5, or sorry, find P if A of 5 equals $400, and then we've got the same growth rate. So again, this all goes back to taking this, plugging in the information you know, and then solving for what you don't know. So in this one, we're starting out with PERT. So sometimes I just write A equals P times E to the RT. It's saying to find A of 5, or if A of 5 equals 400, and we know the growth rate, then find P, the principal amount. So A of 5 is 400. So that means 400 equals the principal amount we don't know. That's what we're going to solve for. E raised to the RT, the point is, or the rate is 0.072, and the time is 5 because we know A of 5 is 400. So now we need to solve for P. So how are we going to solve for P? Right now, P is being multiplied by E by all of this. So basically, if I can just calculate that and divide that by both sides, then easy peasy, and we'll figure that out. So I'll do one step at a time. Say I've got 400 equals P. Okay, so now I'm just going to calculate using my calculator E raised to the 0.072 times 5. When you do that, you should get about 1.433. Let me just double check that really fast because I didn't actually plug it in. Okay, E raised to the 0.072 times 5. Oops. Okay, so when you actually type it in, it's 1.433329415. So I've written this just out of laziness, but when you actually divide both sides by this, use the answer in your calculator, because when you're using values like this, and it does matter that we can be as precise as possible. So now we would just divide both sides by this number. Divide by that, divide 400 by it, and we'll get that, the initial value. So in your calculator, you can just type 400 divided by and then answer, which gives us the most recent value we had, which was this full decimal. And then when I do that, I get 279.07. So that is the principal value. And if I invested $279.07 at a rate of 7.2%, then 5 years later, I would have $400. Don't get your hopes up. That's not going to happen to you because, like I said, that interest rate does not exist at a bank these days or ever. Okay. All right, this next example, I love examples like this because it actually is pretty interesting. If you have a savings goal and you found a bank with a specific interest rate that they'll pay you for creating an account, then you can actually calculate how much you need to invest initially if you want it to grow to a certain amount, or how much you'll have in the end if you invest a certain amount over a certain amount of time. So this is actually kind of cool. And so suppose that when you were born, your parents decided to open a savings account to ensure that you would have $50,000 for your college education 18 years later. So $50,000 is our goal. And over a period of 18 years, assuming the bank pays an annual rate of 4.8%, compounded continuously, that means we're going to use the PERT function. What was the initial deposit? Okay, so we've got a bunch of pieces of information. The fact that it's compounded continuously tells us we're going to use the PERT equation. A equals principal times E raised to the RT. Now it's just a matter of going back and taking all the information from this paragraph and plugging it into PERT. All right, so the A is going to be the end result, and that would be our goal of $50,000. So $50,000 equals P, the principal amount, which we don't know. The question ends with what was the initial deposit. So right away we know we're going to end up needing to solve for P, times E raised to the RT. So my rate at 4.8% would be 0.048 times T It's going to be invested for 18 years. So I need to solve for p, and this follows exactly like the previous example because I can just figure out what that value would be and then divide both sides to get p by itself. So this simplifies to 50,000 equals p times. So now I'm just going to figure out what e raised to the 0.048 times 18 is. And if you haven't used your calculator in a while, the number e is right above your division sign. So, all right, we plug that in, and it's about 2.372. Whatever you get here, leave it on your calculator and use that exact amount when you divide. So now divide both sides by that, and you'll end up with, so 50,000 divided by that answer tells us we should invest an initial amount of more space, $21,073.64. So if your parents were fortunate enough to have an extra $21,000 laying around when you were born and invested it at a bank they were fortunate enough to find with a rate of 4.8%, then you would have a pretty great college fund. So you can go ask them why they didn't invest $20,000 for you 18 years ago. All right. So the next one here, a radioactive substance decayed from 70 grams to 43 grams in 230 years. So that means I've got, if it decayed from 70, that's my initial amount. 243, that would be my new amount, the A. And I know T. It's asking for its decay rate, R. So I have, again, it's decreasing at a constant rate, P-E-R-T. So we're going to start with that, and we plug in all the information we know. So we know that A is 43. That would be the new amount after it had started at 70, and times E raised to the R. We don't know R. We're going to solve for it. And the time that it was decaying was 230 years. So this is going to be a little different because now what we're trying to solve for is right here in the exponent. That's going to complicate things a little bit for us. We can start by simply dividing both sides by 70. If I divide both sides by 70, I can at least get this e to the power by itself. So that means I've got, I'm just going to leave it as a fraction actually, 43 over 70 equals e to the r times 230. Okay, so here we need to think about how am I going to get this r out of the exponent, and this is where using logarithms comes into play. When your variable is in the exponent, you need to use logs to solve. When variable is in the exponent, use logs. Some of you are hating this right now because you don't like logarithms, but they're so useful to us because right now is the only way we can solve a function this complicated where our actual variable we're interested in is in the exponent. So the log with a base of e would be most useful to us here, which means we can actually just use the natural log function and apply it to both sides. So the natural log of this, so I apply the natural log function to 43 over 70, and then I apply the natural log function to the other side as well. Now think back really hard to properties of logarithms, and I'm hoping you remember that when you take the log of something with an exponent, that exponent let me get a different color, comes down in front of the logarithm. So really what we've got here is the natural log of 43 over 70 equals r times 230. That all came down in front and is multiplied by the natural log of e. Well, the good thing for us is that the natural log of e is just 1. So I'm going to cross it out because it just equals 1. And then now I'm left with this big thing right there equals r times 230. So all I have to do now to solve for r is divide both sides by 230, and I'll get my value of r. So you're going to type this whole thing in. I would type in natural log of 43 over 70 first. So natural log of 43 divided by 70. You'll get a negative decimal, and then divide that by 230. And I get an even smaller negative decimal. So I got that r equals negative 0.0021. So think about what that means. Does it make sense for our problem? We were asked to find the decay rate of something, so it should be negative. And it is about negative 0.2%. So you can leave it as a decimal or you can write it as a percentage. And then this last example is using the half-life formula, which is provided here for you. Don't be intimidated by this. Some of you may have used half-life in chemistry or biology, or I don't know when you use half-life, but that's why I teach math. But you've got all the information you need. So strontium-90 has a half-life of 25 years. So that's what we'll plug in here. And how much of a 10-gram sample will be left after 30 years? So that means we know the starting amount, which means, let's see. So that means y equals 10 grams of strontium times 0.05 after 30 years, so that t equals 30. So I'm going to plug 30 in there, divided by the half-life of 25. So that's all of our information plugged in to the half-life formula. So we can figure that out even though we're not using PERT, although we could. We can calculate that from here. So you plug and chug with your calculator, and we get the amount that would remain is about 4.353, and we're talking about grams of a sample. All right, so that is it for our section on exponential functions.